Okay, everybody, welcome back. This is the first IQuS seminar for the new academic year. And today is our great pleasure to have our own Sebastian to talk about the thermal nature and the quantum magic of confining strings. Sebastian got his PhD from Jena in 2020 and did several postdocs training around the world. And now he's acting assistant professor in our department. Sebastian, the stage is yours.
Yeah, thank you very much for the nice introduction. I joined the University of Washington last month, and one advantage of moving is I finally found my pointer after 2 years, and it's the first time actually using it after I bought it. Before that, I was a postdoc in the Co-Design Center for Quantum Advantage at Stony Brook University. And yeah, my talk is split in 2 parts. In the first part, I'll be talking about the thermal nature of confining strings. And this is work in collaboration with Dima and his new graduate student, Eliana. And in the second part, I'll talk a little about quantum magic during string break, which is ongoing work with Martin and Nikita, which are both here. So in general, the question we want to understand, of course, is confinement in QCD. So if I picture a quark and antiquark in QCD that are connected by a color flux tube, when I pull them apart, I need more and more energy. And at some point, so much energy is needed that it's energetically more favorable to break the string apart. And we kind of have a pair production when the energy needed to pull the string further apart is greater than twice the mass of the quark. And this is particle production from the quantum vacuum. And this particle production, they screen the fields that we saw before by the flux tube. Here, as a proxy for QCD, we want to study a simpler mechanism. We'll focus on two-dimensional QED. Instead of the quark and antiquark, we have an electron-positron pair that are connected by a string. And in particular, we focus on the static setup. So we look at this configuration where we put those 2 charges and we compute many, many ground states when we pull those charges apart. So there's no dynamics here. Everything is going to be a ground state. And this gives us a picture of the string breaking process. So first the string is being stretched and eventually it breaks, and we see this at various separation of the external source. Now, there's a lot of pretty impressive literature on the topic, even in 2+1 dimensions, some on quantum hardware. So you might wonder, what's the point of kind of adding another paper to this? And I think one point that's kind of the story here that is or has been a little overlooked is that we want to argue that for a subsystem that's centered in the middle of this string or in the middle of our spin chain, when the string breaks, it looks to the subsystem like the system is thermal. So what you see, the rearrangement that's happening through the entanglement is indistinguishable for that subsystem to actual thermalization or some thermal rearrangement. So the subsystem cannot distinguish entanglement-induced mixing from thermal mixing. And that's what I want to talk about in the first part. You're probably all very familiar with the Schwinger model, which is 2-dimensional QED. So we have fermions psi that couple to a gauge field A mu with electric charge G. And the mass of the fermion breaks chiral symmetry explicitly. If we were to make the fermions massless, then we can solve the Schwinger model exactly using methods from bosonization. However, at finite mass, we have to resort to numerical methods. And the Schwinger model is pretty interesting as a proxy for real QCD, because it has something like linear confinement, which we want to study today. And we can form bound states that are meson-like, like in QCD. To solve the system numerically, we put it on a lattice. So we discretize our system, and by discretizing, introducing staggered fermions and doing a Jordan-Wigner transformation, which I'm all skipping here. So if you're not familiar, maybe stop me and ask questions. We eventually arrive at this lattice Hamiltonian. So the Hamiltonian contains this kinetic part here. Should this one mouse. Right. The kinetic part here, which is a nearest neighbor hopping term. Then we have this mass term and the electric field. And on top of that dynamical internal electric field, we add an external electric field, which are our two external charges. So if you want to picture it as a plot, the setup looks as follows. I don't show you the vacuum, but this is the spin chain where we started inserting the external charge. So we have the electron and the positron. And then we start pulling those external charges apart by placing them further and further apart on the lattice.
What is X and Y?
This here? Those are Pauli matrices. Yeah. X is sigma X and Y is sigma Y. Yeah, and by pulling those charges apart, eventually we'll see the string breaking when we stretched it long enough. So we simulated that numerically. So we have those two external charges, as I just said, that are connected by the confining string. And if you monitor here the potential, so here I'm showing you the ground state energy at separation D of the charges minus the vacuum, then you see that this increases linearly, like we would expect for linear confinement. At some point, this saturates, and this is exactly where the string breaks and it plateaus. So no further energy increase because the field is screened. On the right, I show you, yeah.
But in the end, it goes up again. What happens?
I would expect it's a boundary effect. At some point, those external charges, they reach the boundary. And we use open boundary conditions. So I think the tail you see at the end here is just boundary effects. I should probably stop here somewhere here. Yeah, in the right, I'm showing to you the mass gap, which is the mass of the first excited state, normalized by itself. So as we pull apart the charges, you see that the mass gap is dropping, and it's dropping to close to zero and bottoms out here, where the string breaks, and then it increases and eventually plateaus. I should maybe say our system is rather large here, so we used 220 points, and M over G is about 1/2.
Is this obtained by tensor network?
Yes. Yeah, this is obtained using matrix product states. Otherwise, you need like a quantum computer. Yeah. So if you look at the energy density and the charge, then you actually see a very beautiful plot. So let me explain to you what you see here. So on the left, you see the energy density, and the spin chain is along the y-axis, while the separation of the sources is along the x-axis. So here are the sources introduced, and then you see the string building up, and the energy is flowing along the string until the string breaks and everything is being screened. So you see this cloud around the charges that immediately screens the field. So here you can actually see the string breaking process in the energy density. The same for the charge. You see the external, if we are measuring the charge across the system, then you see the propagation of the external charges here as we pull the two external charges apart. And when the string breaks, the charges get immediately screened because we have those dynamic particles that were being created during the string breaking process. Yeah.
So the x-axis is the distance between
charges,
and
yes.
the y-axis is just where they are on the lattice.
Yeah, the y-axis is the lattice. Yeah. That's why it's it looks like a light cone here. Yeah.
Is this banana coupling dependent? Like if you change the prime?
Yes, if you
Mostly.
change, yes, the string either breaks sooner or later if you change the ratio of m/2. Yeah, and initially you have the screen, and then the string breaks into a pair of non-interacting mesons if they're far enough apart. Yeah. No, this is just the static process. Yes, each vertical slice is a different ground state, so it's a different configuration. Yeah, that's why there's also nothing in between those two. Because if you do it dynamically, you pump energy in the system and you have a lot of stuff flying around in the middle. But if it's really a static configuration, then it's screened and there never was any energy there.
So it looks in the, before it breaks in that early region.
Yeah.
It looks like, so I always, in my head, if it breaks, there's like basically a straight line where it goes from connected to unconnected, and it looks like it kind of arcs a little bit. Is there like, I guess what's the interpretation of that? Is that meaningful?
Yeah, it's not a straight cut. So what's happening is if you, I can show you a slide at the end of the talk. I have like the cuts, how the energy density looks in 2D. I think it's better to see it there. Maybe you can ask later again. I can show you the slide.
Probably the nuclear force in the head.
How so?
Because when they're sort of within an interaction region, they have some sort of distribution. They're not quite separate.
Yeah, they're not, yes, okay, yes. Yeah. Yeah, they're only non-interacting if you pull them apart far enough.
It is interesting how it broke.
Yeah, I mean, yeah. So what you can also look at is the condensate in the middle of the lattice, and this is the condensate on the middle 2 and 4 sides. And you see how the condensate builds up as the string stretches, and when the string breaks, it immediately starts falling off kind of exponentially and goes to the vacuum value. The same for the electric energy, which increases linearly as the string is stretched, and then it plateaus to a value during the screening. Okay, now, so far I looked at intervals exactly in the middle when I showed you the condensate, for example. To compute the entanglement, we can look at two different partitions. So we could look at the entanglement of the subsystem in the middle of the lattice, like shown in the left here, with the rest, or we can look at the entanglement entropy of the left side of the lattice with the right side. These are just two different partitions. And when you do that, so on the left, I show you the entanglement entropy of some subintervals in the middle of increasing size as a function of the separation. So the smallest interval, you see the entanglement entropy turning and even turning negative before it goes to the vacuum. While when the intervals become larger, it more and more looks like the half-space entanglement that's shown on the right. And in the half-space entanglement, you again see very clearly the peak where the string breaks, and then it falls off to the vacuum when you have the non-interacting mesons. Okay. Yeah.
Sorry, I want to ask you how the entanglement interface cosmetic. Oh, it's some difference.
It's the difference. Yeah, the vacuum is subtracted.
Nice.
And yeah, it's the difference. Okay, and yeah, let me come to the entanglement spectrum. So what you see here are the different Schmidt eigenvalues. So we take the reduced density matrix, we diagonalize it, you get all those eigenvalues, and those are the eigenvalues where you compute the entanglement entropy from. But I'm showing you those eigenvalues here directly as a function of the separation. And what you see here in when the string breaks, the entanglement, the gap in the spectrum closes exactly where the string breaks. So there's a dominant eigenvalue and the subdominant eigenvalue increases and then they cross. And after that, the second eigenvalue, the second most dominant eigenvalue becomes the dominant eigenvalue. And if you look at the lower ones, they also start all peaking, and near the spring breaking, the entanglement spectrum becomes pretty flat. So here it's gapped with two dominant eigenvalues, the rest is suppressed. But at the string breaking point, all those eigenvalues, they move up and I have a much more flat eigenvalue spectrum.
Do you read anything of the fact that the large eigenvalues sort of become flat almost immediately, and then the smaller ones take a while? When they sort of different realizations of it.
Yeah, I'm so we haven't worked it out, but I'm trying to separate them by charge sectors. So it looks like the different charge sectors peak at different times. That's why it takes this why those peaks are at different distances.
So the relaxation is just related to the different sectors.
Yeah.
I'm wondering about you have string breaking, time reversal, strings to come together. So it could be terms where the string breaks, comes together, and then breaks again. That how is that in the number?
Well, there's no dynamics here, so there's no time going. Those are static configurations. I think if you're at the point where the spring breaks, you're basically in a superposition of a state where the spring is broken and not broken. And after that, it's pretty clear what's thermodynamically favored, either the broken spring or you still have the spring.
It's here that the charges are pulled apart by default. We put the charges there. There's no dynamic that we know we can.
Yeah, you basically
Put it there and
And measure the energy. You put charge there and measure the energy.
you have your ladders, you put two charges, one here, you compute your ground state of the configuration. That's one thing. Then you put the charge here, and here you do the same again. And that's what the distance in the plots is. So this is one configuration, this is another configuration, but you're not dynamically going from one configuration to the next one. Yeah, and yeah.
I think you just answered the question on someone, but if I were to just look directly at those states that come from that diagonalization, those
Yeah.
have the qualitative features you just described, like try to think of the energy that
I think how we want to interpret this is at the crossing here. So initially you have a state that favors the string, and then the state that has the E plus E minus pairs, the two mesons, is favored, so it becomes the most dominant eigenvalue. And yeah, if you look at sector weights, so you can kind of take that apart by charge 0, charge 2, and so on. Then you see near the string breaking, there's a peak of charge 2, but before your charge 0, after your charge 0, but it kind of goes down while the other one goes up, and then they go back to the charge 0. So there's some mixing in the charge sectors. I think I also have a plot for this. Yeah, any more questions about the spectrum?
It looks kind of like a D from 0 and then D on the far right side.
Yeah.
It kind of looks like, you look at the I largest level, and they swap, but they kind of end up going to the same value approximately for all of them. Is that meaningful in any way? Is it like the relative like distribution of states you have pre and post breaking is the same, but the degrees of freedom kind of like change with one another?
Yeah, I think that's fair. Okay, yeah, on the weekend, instead of preparing the slides and practicing the talk, my brain started obsessing about multiple string breakings. So it's just an aside. You can break the string how often you want if you put enough charge. Here you break it twice, your reward is 2 peaks, and you see those 2 crossings in the entanglement spectrum. You can take it to 3, 4, whatever you want. Was it
What did you change to get the 2 string breaking?
I put more charge.
You put more target.
Because if you put only the 1 pair, then you can break it only once.
Right.
But if you put more charge, then you can have a partial breaking and then you can break it again. Yeah, and this is another side remark. So you can look at the entanglement entropy, but symmetry resolved. So this is the entanglement entropy for an interval of size 32 in the middle of the lattice. But I look at different symmetry sectors of the charge. So if you have your reduced density matrix, you can write it in different charge sectors. There's charge 0, there's charge 2, charge 4. And within that charge sector, I can compute the entanglement entropy. And yeah, if you sum them up, this is not the actual entanglement entropy. It's something different because the actual entanglement entropy is a configuration entropy, which describes the entanglement between charges. And then you have the symmetry resolved entanglement entropy with a sector weight. And this is not shown. So this is really the entanglement entropy within a charge sector when those charge sectors are most mixed. And this appears in a very peculiar order. So first the charge 8 sector peaks, then 4, then 0, which is kind of n half is even. And then the sectors with n half is odd. And yeah, the only thing I really understand about this plot is the charge 2 sector. It's maximally mixed when the string breaks, and then you get your meson here. Why the rest is in that order, I don't understand yet. But it's just a side remark. So now let me come to assigning some effective temperature to the string. So this is a technique we introduced in this paper here. And basically we want to assign the system an effective temperature by comparing two thermal states. So what we do is for a given state, we pick a subsystem A, which is for example, in the middle here. And we can compute the reduced density matrix of the subsystem. In our case, it's the subsystem with the string or with the broken string. This gives us one quantity. On the other hand, we can compute thermal wave functions, which are characterized by temperature for a system of size, let's say N2. And for those thermal wave functions, there's no external source present. So those are really thermal wave functions. And we can compute thermal density matrices from those thermal wave functions. Then to assign a temperature to our subsystem L in the middle here, we compare the reduced density matrix to the thermal density matrix by computing things like fidelity or trace distance. Is that clear?
Where is the black? Two circles in open space.
So this just it's a staggered fermion. So two of them are one physical size. You have like fermion, anti-fermion. That's why they are color different.
But how did you deal with the different charge sectors? You take the same distribution for the different charges?
The same.
Like the reduced density matrix of A.
Yeah.
As you explained in the previous slide, is the Q equal 8, 4, 0.
Yeah, this is now all charge sectors. This is the full reduced density matrix.
Right, but different charge sectors don't mix with each other. Right.
Yes.
And so your thermal state, right? The step 3 you have there. When you write down the thermal state, right? You need a homotonic.
Yes.
And that requires the boundary condition. Right, you can set Q equal to 8 or 4.
Yeah.
So are you using all of the boundary conditions in some algorithm? with some,
So to get rid of that, I generate the thermal states for a larger system. And then I trace out the boundaries so that the boundaries hopefully
you
don't
do
matter.
the same,
Yeah.
iPhone.
Yeah, it's basically a reduced thermal density matrix.
I see, I see.
So-
So the thermal state leaves out B plus A,
Yeah,
but then you trace out the B again, okay. Yeah.
not exactly B plus A. I wish I could do that, but I can't. But on N2, which is some number larger than L,
But I see, but smaller than the total
but
size of this.
smaller than the
Yeah.
total size.
Okay.
And then N2 is traced down to L so that they have the same size, and then you can compute the overlap.
Why can't you? Why are you supposed to set M2 and not the solar system?
Because of boundary effects. So I don't want to have any boundary effects, because if I generate the thermal wave functions, there's necessarily, since we do open boundary conditions, there are some boundary effects. We can choose different boundary conditions, and I want to reduce those effects, so I'm just tracing out the sides. And it does make a difference, especially for the vacuum. Okay, those two plots, they basically show you the same thing. So in the left, I show you the ratio of purity of the reduced density matrix to the purity of the thermal density matrix at the temperature where there's the maximal overlap between reduced density matrix and thermal density matrix. So basically, I computed all overlaps for all temperatures, and then I pick the temperature where the overlap is maximal. And this is what I call temperature at the given distance. And if you plot those purity ratios, then you see they match almost exactly at around where this, shortly after the string breaks. So the string breaks at around 7, there we go pretty, and then they basically go to 1. So they have a matching purity. On the right, you see the participation ratio, which is basically just 1 over purity. And again, those match exactly at distances where the string breaks. So the entanglement entropy, it creates some rearrangement of the degrees of freedom, and this rearrangement looks to the subsystem exactly like thermal rearrangement. So when the string breaks and those match, the subsystem cannot distinguish whether we thermalized or this is just a static state where entanglement rearranged the degrees of freedom. Which kind of means that entanglement might be responsible in the first place for the thermalization that we observe with string breaking. Okay, if there are no questions, then we can plot the temperatures that we obtain from those overlaps. And we looked at 2 different measures. One is the Hilbert-Schmidt distance, which is a proxy for trace distance, because trace distance is pretty hard to compute. And instead of computing fidelity, we compute normalized overlaps, which should be on the slide, but it is not. Anyway, the temperature extracted from the overlaps is the blue curve, and what you get from the Hilbert-Schmidt distance is the red curve, and they match pretty closely. And what else you can see in the plot is the energy density shown in green here. So the energy density peaks when the sources leave the subsystem. So here, this is the point where the external source leaves the subsystem of size 8. And then the fall of the temperature matches exactly the fall of the energy density. And when you look at the right plot, this is the maximum normalized overlap or the maximum complement of the Hilbert-Schmidt distance. Then you see you're the closest to a thermal state at the point where the string breaks. So this metric is kind of maximized exactly at the point where the string breaks, which again points to the fact that at the string breaking, the system looks kind of thermal, the subsystem. Yeah, now let me come to the second part. How much time do I have?
Maybe 12 minutes.
Yeah, okay. Well, you don't see it very well.
Why do you use, single model instead of the Prof model? A similar model, 1+1. What makes it one easier than the other?
I have to think about that one. Yeah, the second part is about quantum magic. And quantum magic basically describes how far we are from a state that's efficiently simulable on a classical computer, or how far we are from a stabilizer state. So what's a stabilizer state? So if you look at pure quantum states, then we can define some stabilizer group, which is a subgroup of the Pauli group. And the Pauli group are just the Pauli matrices as a string on your lattice system. And the stabilizer state satisfies G, where G is an element of that stabilizer subgroup. When it's acting on the state, then you get the state back. And there's a theorem here that for those stabilizer states, they are very efficient to simulate on classical computer. So when we want to make resource estimates for how difficult it is to simulate things classically and where a quantum computer might have any advantage, then we should look at how much magic those states have. And a magic state, for example, is a state that's not a stabilizer state, and it includes things like non-Clifford gates, like a T-gate. And if we have those states, they need the stabilizer manifold that was defined by this subgroup here, and they become non-stabilizer states or magic states. And the more magic a state has, the more difficult it is to simulate it classically. So if you want to have a quantum advantage, then you should look for states with a lot of magic. This is a bit technical. So one measure to kind of characterize quantum magic is the stabilizer entropy. And this provides a concrete measure for quantum magic, and it's defined like this. So you have your expectation value of your Pauli matrices, and you sample them across your whole system. And there's an algorithm how to do this with MPS, but I think it's too technical to explain. There's another measure that's a lot easier to look at, which is called anti-flatness, and it's related to the entanglement spectrum. And anti-flatness characterizes how far from flat the entanglement spectrum is. So it's defined as the trace. Here you have your reduced density matrix cube minus the purity squared. So this is a particular combination, and this combination vanishes, for example, if you have a pure state that only has one eigenvalue, then trace of rho is 1, and this is also 1, so you get 1 minus 1 is 0. If you have a maximally mixed state, which is the identity divided by the dimension, then again, if you plug this in, you find 0. So this anti-flatness vanishes for pure states and for maximally mixed states. And it kind of gives you a measure how non-flat your entanglement spectrum is. This whole measure is related to magic because stabilizer states, they have very constrained spectra. The reduced density matrix is block flat across the Pauli sectors. So you get states which basically have 0 anti-flatness.
Not Pauli sector. You mean
you can write it in the Pauli basis, and then you get block flat means it kind of decomposes in the Pauli basis diagonal with some constant prefactor. And those would factor out, and you would find either zero or a very small value.
How many poly sectors are there?
It depends on your system size, right?
But I guess it cannot be as large as system size. You have different.
Yeah.
You need to have a lot of them having the same quotation.
Are the power sectors, are those related to the generators?
Yes, exactly. You can write it in terms of those generators, and that's why it's block diagonal in the polar sectors. Which exactly happens for the stabilizer states, where when I'm leaving that manifold, I cannot write it in terms of those generators. So I get mixing between the different sectors. And this mixing introduces the non-flatness. Yeah, what we were kind of wondering is what happens to quantum magic during the string breaking process. So I'm not sure if you have any guesses what you would expect when there's the most magic and when there's the least magic. So yeah, what do you think is best, easiest to simulate?
During this whole.
Yeah.
Probably when you're not breaking the string. So when you pull them far apart.
Yeah, let me draw it. So we had this resistance, the entanglement, and the field something like. So how do you think the magic looks?
Magic will also have a peak structure before the peak of the
Okay, and what does it what does it do before?
grow.
So you guess it looks like this, and then
No, the peak doesn't.
the decrease. Okay. Before or after?
I think it's. Yeah.
Any other guesses? Yeah, why do you think it's before?
Oh, I mean, we just did the calculation and here last night. But it's real-time dynamics. It's not the equivalent charges apart. But in real-time dynamics, we saw the magic peak appear, or the anticlimactic peak appeared before the entanglement.
Yeah. Well, in the static case, something. Okay, let's skip this. Okay, let's get to the plot. So in the plot, you see the magic in blue, the entanglement entropy in red, and the anti-flatness in green.
Very different. Yeah.
Okay, so this is a scale plot. It has two axes. If you want to see how it actually looks with absolute values, it's on the right. So here I subtracted the vacuum values, and then I put anti-flatness and magic on this left axis, while the entanglement entropy is on the right axis. So what you see is that the magic goes down until just before the string breaks, and the magic peaks with the entanglement entropy, while the anti-flatness peaks just after the entanglement entropy peaks. Yeah. The entropy is not negative. The entropy is the red. Because I subtracted the vacuum. So even the vacuum is not flat, right? Because you look at the reduced density matrix. So you have a vacuum state, but you trace out a lot of your system. So this is already a mixed state that has some entanglement spectrum with a certain structure.
Okay, so it's an opposite.
Yeah, here in the left plot, you see it starts at, I don't know, 0.8 or something, then it goes down to 0.2, and then it starts peaking.
Okay, my point is, if I take into account the offset, it's always positive.
Yeah, if you take the account, yes, it's always positive. You take the offset into account. Yeah. Well, it looks like it's the easiest to simulate the spring, or it's the most classical just the void break. So when you stretch it, it seems to become easier and easier. And the fully stretched spring seems to be the easiest setup. No. Yeah, no, we're still trying to figure out what's going on here. It makes sense that it peaks kind of around where the entanglement entropy peaks, because then you have that quantum superposition of broken string and classical string. But yeah, I'm not sure why it's the most classical when you have the stretched string. But yeah, just maybe the last minute. You can also do that dynamically. So here we pull the sources apart as a function of time, which also appeared in those papers. And then you can compute the anti-flatness for this kind of setup. So here you see the entanglement entropy of an interval in the middle versus time. The entanglement entropy is flat while the sources are still within the subsystem, and then it increases with an area law. And at late times, you see thermalization, and the entanglement entropy shows a plateau. If you look at the anti-flatness compared to that, then the anti-flatness drops rapidly from the vacuum state. It reaches some minimum. Then there seems to be some magic barrier. So the magic builds up to a certain point. And then when you thermalize, the magic drops and reaches some minimum, which also kind of makes sense. Yeah. That I cannot tell you. So this is the dynamic process, and it's very hard to say where you have the spring breaking.
What do you mean?
The initial state is the vacuum.
Strongly.
Yes.
So it's not the interaction vacuum state, right? Otherwise it doesn't.
It does. So it's the vacuum state, and then at a certain time, the external source is put into the system, and that perturbs the yes, you quench the system. Yeah. You can measure the charges, but it's also not very clear. So because you continuously pump energy in the system, there's a lot of stuff lying around. And if you look at energy density or charge, there's no clear plot where you can see the spring breaking. Yeah.
So when you said you dynamic, you start from
No, you start from the vacuum, and then after some time, you switch on the external charges as a quench. And that introduces the dynamics. And then you forcefully pull the charges apart.
Okay. I guess I was wondering if the oscillation in it's like if you look at that expectation value of the different two charges, you would oscillate. It would oscillate, and you would oscillate.
So yeah, so the sources basically they're pulled apart in. Let's go back here. So the sources are being pulled apart in integer steps. So at time 1, the charges are placed into the system as a quench. And at time 2, you move them 1 apart. So here the distance between the next 3. At the next integer time, we keep moving them apart. And I think the oscillations are related to those basically steps in your sources.
So the sources themselves, they're always just going.
Yeah, but basically in integer steps. So you move them apart, then you wait until the next integer time, and then you move them apart one at a time. Yeah. Okay, with that, I come to my conclusions. So I showed you a microscopic model where we can see that thermodynamic behavior. No, that's not what I wanted to say. Where you can see that thermodynamic behavior already emerges in the static case. So when the spring breaks, we get closer to something that actually looks thermal without doing any dynamics. Yeah, this approach may be inferred from the static setup. And then we started exploring the quantumness of the string breaking process, and also the theta vacuum, which I don't show you here to not mix in more things. And there are lots of interesting things to do in the future. Yeah, thank you for your attention.
Sebastian, thank you very much for the very interesting talk. We already have a lot of discussions in this room, so I'd like first ask if there are any questions from the online participant. Yeah, I didn't. If you want to ask a question, you can just unmute yourself. Okay, I didn't see anything, so let's get back to the room. Any question for Sebastian?
In the earlier version, we were showing for each type of population density.
So those ground states, you have your discretized spin Hamiltonian, then you use matrix product states, and it's basically a DML tree.
And you put in the external charges.
Yes, you put in the external charges in the Hamiltonian. Basically, you have your normal electric field of the Schwinger model Ln, and then you add this external electric field.
You just started with where the 0.0 from the or you also have to do the
Are you asking about the dynamics or the static? Yeah. Yes. Yeah, the external electric field is basically given by this theta function. And it returns 1 in between the two charges because you put the charges on the link. So basically everything where that red string here is returns a value, and that's how the simulation sees your external field.
So later this year, GL will tell us how to put non-abelian charges on the value.
So, okay, so I'm not too familiar with quantum magic, but so if you want to have some sort of, say, like circuit or process, what that is, takes advantage of a low magic state that does something that's like possibly simulable,
yeah.
Then you would have to do a circular Clifford operation.
Yeah.
So are there some sort of process for these for like the Schwinger model, for these ground state Schwinger models, where I actually want to do some Clifford circuit or something where I could take advantage of the computational simplicity of some of the states that they
Yeah, that's what we want to explore. So we want to explore how this quantum magic kind of translates into circuit depth, but we haven't looked into that yet. And it looked like, if we look at the time evolution, then the ground state looks kind of the hardest, right? Because it has the largest anti-flatness. As soon as you start time evolving, this drops rapidly. And it seems to be much easier to simulate.
So the question, yeah, maybe for the audience, it's maybe the silly question, but is the time evolution Clifford or?
It's just Hamiltonian time evolution.
So I guess for time evolution, then wouldn't you just like, if I started with a low magic state, I mean, I would kind of lose control of the computational simplicity pretty fast. Yeah, is that true?
But well, here it seems to be the opposite, right? I start with a complicated state, and then it becomes classically much easier.
Real.
Yeah, well, I guess it needs like, it seems to me, at least in, maybe you're thinking the fault tolerance perspective, but I would have guessed that for current devices and near-term devices, the entanglement entropy would be a much better proxy for circuit depth than magic flow. I guess I don't see, or at least I understood what you meant, like looking at the magic and anti-flatness that can help you understand what the circuit depth is. I guess, what is the motivating thought behind that?
Well, ideally, so in my mind, if you want to have some quantum advantage, you ideally start with like a state that has very low magic because you can prepare it pretty easy. And then you want to get something that becomes very hard to simulate classically, because that's where you get your advantage. So I think it makes sense trying to map out how kind of magic translates into circuit depth, for example, or where your system is very efficiently simulable, or where the regimes are that are hard to do. So I think in that sense, if you think about trying to achieve quantum advantage, it would make sense to me, trying to find something that's very low magic as a ground state preparation, and then do something that's really, really hard to do classically.
If you look at the pattern stuff, optimization,
You mean here?
Yeah. So what I need is in which sense you talk about what you mean by normalization concept.
Yeah.
So it's the first by this.
So, yeah. Yeah, so what I'm saying is that the reduced density matrix looks like a thermal density matrix.
So that the eigenvalue distribution follows
Yeah.
that also.
Yeah. You can literally compute something like an overlap between the two, or fidelity, and it goes to 1 when the string breaks. So you cannot distinguish your reduced density matrix from the thermal density matrix.
Because I was thinking of something that happens in quantum system, which is zero thermalization.
Yeah.
And there are two more cases, different cases we talk about thermalization. One is when you have a state, doesn't matter how the state is done, which is following the operation with spectral relation. And since here you have some forces because you are moving the charges,
yeah,
it would be interesting maybe to investigate if this state satisfies the operation with spectral relation.
Yeah.
So you need to compute the value to check this, check that when you put a force into your system, you just check how that fluctuation responds with your projection. And also the other way to look at the normalization is that well, basically the point is that you cannot distinguish it from a state by what you can observe,
yeah,
even without looking at the perspective. So it was more common than a question.
Okay.
That maybe there's some interesting things to look at, but
Why is it pseudo thermalization? Why the pseudo if it looks like thermalization?
because the state does not look because
Okay.
the point is that the state is something else.
Yeah.
But if you look at how this state responds to an external input,
yeah,
and follows the same fluctuation relation to the thermal state, then produce thermal overall.
Yeah.
But you can tell that it is not thermal.
Yeah.
It's like pseudo.
Yeah.
So pseudo magic, pseudo family state, there's a whole family of pseudo stuff in quantum information.
Okay, I see more questions. So let's thank Sebastian again.